Hi, we're going to talk about directional derivatives and the gradient vector. This is section 14.6 in the Stewart textbook. First, we'll talk about the gradient, then we'll introduce directional derivatives, then derivatives along paths. Then we'll talk about the geometry of gradients and tangent planes. So let's get started. If f is a scalar valued function, then the gradient of f, which is denoted grad f, or this upside down triangle, which is just called gradient of f, is a vector. So f is a scalar valued function, but the gradient of f is a vector. And you can see here that the entries of the vector are derivatives of f. And in fact, they're all the first order partial derivatives of f, however many variables there are. So if f was f of xy with two variables, then the gradient would have two entries. If f was f of xyz with three variables, then the gradient would have three entries. Or however many variables there are, the gradient has that many entries. But having said that, we typically stick in this semester, we're going to stick mostly to two or three variables. So, for example, if f of xyz was x squared plus y to the 7th plus z to the 5th, then the gradient of f would be a vector. We would take the partial derivative with respect to x. That's 2x. Next, we would take the partial derivative with respect to y. That's 7y to the 6th. And finally, we would take the partial derivative with respect to z, and that's 5z to the 4th. Another example, if g of xyz is x squared times y to the 7th times z to the 5th, then the gradient is the vector 2x y to the 7th z to the 5th, 7x squared y to the 6th z to the 5th, 5x squared y to the 7th z to the 4th. An example of a problem that involves gradients, say f of xy is x cubed minus 3xy squared, and g of xy is x squared plus y squared. And the question is to find the xy points where the gradients of f and g are parallel. This is actually foreshadowing something that's going to come up in a later section when we talk about optimization and specifically Lagrange multipliers. So this is foreshadowing something we're going to do later. But for right now, let's just solve this problem. So the gradient of f is the vector 3x squared minus 3y squared, and then minus 6xy, and the gradient of g is the vector 2x, 2y, and we want them to be parallel. So we should have that 3x squared minus 3y squared is 2x. So, we should have them be parallel, like gradient of f should be gradient of g times some scalar multiple. Let's say lambda. So we'll have 2x times lambda, and then minus 6xy should be 2y times lambda. Right, so on the left-hand side, I've got the entries of f, and on the right-hand side, I've got the entries of g times lambda. The gradient of f is the gradient of g times lambda. So here we have two equations, and we want to try to solve them for x and y. It looks a little bit involved, but if you look at the second equation, there's some hope here. We could put everything on one side. So 2y lambda plus 6xy equals 0, and that factors 2y times lambda plus 3x equals 0. And that means that y equals 0 or lambda equals minus 3x. All right, let's look at each of those possibilities. If y equals 0, in the y equals 0 case, all right, the second equation is all fine. What about the first equation? In the first equation, if y equals 0, then we get 3x squared equals 2x lambda. And we can put that all on one side and factor it. We get x times 3x minus 2 lambda equals 0. So then x also equals 0, or 3x minus 2 lambda equals 0. So in other words, then lambda is 3 over 2x. So from y equals 0, we got y equals 0 and x equals 0, or we got y equals 0, x can be anything, and we figured out what lambda was, although we didn't really ask for that information, so we got some unneeded information there. So we're not done yet, but we already know that we can have y equals 0 and any x value. So these are the points along the x-axis. What else? We had lambda equals minus 3x as a solution to the second equation. What happens if we put that into the first equation? Then we get 3x squared minus 3y squared equals minus 6x squared. I wrote x to the 6th, but I meant x squared. So if we add everything onto one side and divide by 3, there's a common factor of 3 all over. If we divide by 3, we would get 3x squared minus y squared is 0. And that factors as square root 3x minus y times square root 3x plus y equals 0. And that means that either y equals square root 3x or y equals minus square root 3x. So we get two more lines. We get a line with slope square root 3, and we get a line with slope minus square root 3. Y equals minus square root 3x. And if you remember your unit circle and the tangent values, those are equally spaced at 60-degree angles all the way around. So those are the three lines where at any point on here, on these lines, the gradients of those functions turned out to be parallel. Well, okay, so we went through that whole example, and I guess I should say that we used gradients at the very beginning to write down these vectors, and then write down the vectors being parallel, meaning there's a scalar multiple. But after that, all the work, none of this work was really calculus, right? All this work that we did in this part of the page was just algebra, just solving some algebraic equations. The gradient part came up at the beginning just to set up the equations in the first place.